This section is on vectors. Before we talk specifically about vectors, I'd like to introduce the general concept of tensors. Tensors come in different orders. The most familiar one is a tensor of order 0, which would be a scalar. A scalar is simply a quantity, such as to describe temperature or speed, like 71 degrees. This has only a magnitude and no direction associated with it. You don't have 71 degrees north, just 71 degrees. Now when we get into vectors, a vector is a tensor of order 1, and that would describe something such as velocity, where you have a magnitude and a direction. So 20 miles per hour going north-northwest, speed would just be 20 miles per hour. Now for a vector, this order 1, you have, say, two numbers are lined in a matrix of just this single line or single column. We could extend this tensor concept further to an order 2, which would be a matrix, where now you have a two-dimensional array of numbers, so it's order 2. And examples of this would be a stress or strain matrix to describe a rock face in geophysics. You can even go to a tensor of order 3 where you have a parallelepiped of data. So we take this table, we extend it out a third dimension, and we can cut into it different ways to get different information. We're going to focus, though, just on vectors. Okay, so scalars have magnitude but no direction, but things such as force, displacement, or velocity have a direction and a magnitude, and they can be represented graphically by directed line segments. So this is not an array, it doesn't go on forever. It's a directed line segment, starts at point A, ends at point B, AB with the little arrow on top, and the magnitude is the length of this directed line segment, and the direction is whatever direction it's going is. And the length is given by these vertical bars around it. Oftentimes you see two vertical bars around it. So here's the vector. Vectors are equal if they have the same length and the same direction. So you can pick this up and move it around. As long as it's the same length, then it hasn't changed direction. It's the same vector. So one thing we often do is pick it up and move it around to standard position, where the initial point is now at the origin. And when we do that, we call this the component form of the vector. We use these triangular brackets. V1, V2 are the two components. So V1 is the x distance. V2 would be the y distance. If we want to find the magnitude of this vector, we simply do the Pythagorean sum of the components, because we would in fact have a right triangle where you would have V1 along here and V2 here. You do the Pythagorean sum to get the magnitude. So if we take this vector here, vector P, which goes from -3, 4 to -5, 2, if we want to get component form, we subtract terminal point minus initial point. So -5 minus -3 is -2, so 2 to the left. And 2 minus 4 is -2, so 2 down. So this vector PQ is equivalent to vector V, -2, -2. Here it is in component form. And then to find the magnitude of it, we do the Pythagorean sum of the components, and we get 2 radical 2. If a vector has length 1, it's called a unit vector. If it is 0, 0, it's the 0 vector, and it has no direction. So different vector operations. If you have the vector U, U1, U2, and vector V, V1, V2, and K is a scalar, you can add two vectors by adding the components individually. So you add the x components and the y components individually. You can subtract them by subtracting components individually. And we'll look at how to add and subtract them graphically in a moment. Scalar multiplication. If you multiply by a scalar, you multiply the components individually. And what this does is it keeps the direction the same of the vector, but it dilates it. It makes it longer or shorter depending upon the value of k. And if you take a vector and you multiply it by -1, it just turns it in the exact opposite direction. So here we have a static version of adding two vectors. Basically adding V and U, you do this concept of head to tail, and then the resultant, which is the overall vector, is the diagonal. And so taking a look at adding the vectors, we see that over here we've got vector A and vector B, and if we want to add the two, here's A plus B. We move them head to tail, and then our overall resultant would be from the initial point of A to the terminal point of B. Now, vector addition is commutative, so we could, instead of doing A plus B, we could just as easily do B plus A, and we would get an equivalent vector. So now we go initial point of A to initial point of B to terminal point of A, and this vector is equivalent to the first one. As far as subtracting vectors, the easiest way to think about subtracting vectors is to add the negative. So if I want to do A minus B, I do a plus negative b. So a, and then I put b on top of it, and negative b is the same length in the opposite direction, and so I do a plus negative b to give me a minus b. Now in this sketch it's a little bit busier, there's more on here. We can see here's a plus b, and as I move this vector around, of course if I have it going the exact opposite direction in the same length, then a plus b is, well, nothing. If I have them on top of each other, then it's the same direction and twice as long. We can also look at dilations. Here this arrow represents the unit vector. This arrow is the unit vector for A. If I want to dilate, say, vector B, I can do, now it's twice as long in the same direction. Now it's 3 times as long in the same direction. It's off the screen now. There it is. So I can reduce the size of it. There we go, and make it now much longer. Or if I go back the other direction, if I make this negative, now it goes the opposite direction. So the scalar dilates the vector. Longer, shorter, can change the direction of it. Some examples in the textbook. So here we see equivalent vectors. They're all the same length, all the same direction, just moved around. This example takes two initial points, initial and terminal point P to Q, and then also R to S, and you find the two individual vectors and realize that they're equivalent because they've got the same magnitude using finding Pythagorean sums, and they've got the same direction, in this case by using the slope to find that direction. This is subtracting terminal from initial, initial from terminal to get the vector in component form, and then once again find the magnitude of the vector, unit vector and zero vector, as I mentioned before. Another example, finding component form of a vector. Feel free to pause the lecture if it's too quick. Here again is adding the vector's component form and then adding it graphically as I showed you before, adding head to tail. Scalar multiple dilates the vector. Vector operations, really quite simple. 2v, you just multiply each component by 2. 2v minus 3w, you would simply do twice the vector v minus 3 times the vector w, and you do the x's and y's individually. Here are some properties which we generally don't use very often, to be honest. Adding the zero vector doesn't change anything. Vector addition is also associative, that sort of thing. Here's the idea of a unit vector. If you want to find a unit vector is length 1, find it in the exact same direction as the original vector. Then what you do is you take the vector and divide it by its own magnitude, ensuring it has a length of 1, but it's going in the same direction. So example of finding a unit vector, you have the vector negative 2, 5, and find a unit vector in that direction. So we find the length of it by doing the square root of negative 2 squared plus 5 squared to get rad 29, and we divide the vector by its magnitude to get to here, and so it's the same direction, but it has a length now of just 1. Standard unit vectors is another way of representing vectors. We have the vector I, which is 1, 0, and the vector j, which is 0, 1, and here they are shown visually. And so instead of writing in component form v1, v2 with triangular brackets, we can write v1i plus v2j. The component form is more convenient, it's less to write, but this is just another way you'll sometimes see it, especially as you get to higher mathematics. So for instance, if we have initial point 2, negative 5, terminal point negative 1, 3, first we get it into standard form by subtracting the components to get negative 3, 8, and then simply that becomes negative 3i plus 8j. So here we are, once again, using simple vector operations, 2u minus 3v, and you handle the x's and the y's individually, in this case the i's and the j's individually, to get the overall vector sum. Well, in this case, a vector difference. Direction angles, going back to a unit circle and realizing that the x is the cosine, x is related to cosine, y is related to sine, we can write a unit vector in terms of direction angle as cosine theta I plus sine theta j. And with that sort of thing, what we can do is to find a direction angle for this vector, because the direction angle is from the horizontal going in the positive theta direction here, counterclockwise direction. We can find that angle by doing the inverse tangent of the j component divided by the I component. So here we get 45 degrees. for this one, 3i minus 4j, inverse tangent of negative 4 over 3, which is negative 53 degrees, and you can add 360 if you want it between 0 and 360. Basically, it's the inverse tangent of the y over the x components. The only difficulty here is when you are in the second or third quadrant. That is when the first component is negative. You've got to add 180 because inverse tangent only evaluates in the first and the fourth quadrants. In this example, we're finding the angle between these two vectors, 1, 1, and 2, negative 2. So I graph them. Here's 1, 1, the blue vector. 2, negative 2 is the green vector. I can find the length of this third side of my triangle by realizing that it would be, if you imagine another triangle here where it's across 1 and up 3, so 1 squared plus 3 squared is equal to c squared, I get rad 10. And so now I've got radical 10 for the third side. Well, to find the angle here, this is side, 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 I can use the law of cosines. And so plugging in the numbers appropriately, I have rad 10 squared is equal to rad 2 squared plus 2 rad 2 squared minus 2 times rad 2 times 2 rad 2 cosine theta. And solving this for cosine theta, I can go on and realize that it's actually 90 degrees between those two vectors. In this example here, I'm given the vector 6i minus 6j. I want to find the magnitude and the direction. The magnitude is the length right here of the actual vector. So here's the components. Here's the 6i part. Here's the negative 6j part. So to find the magnitude, simply Pythagorean sum of the components. So the magnitude of v is given that way, rad 6 squared plus negative 6 squared, which gives me 6 rad 2. To find the angle theta, I know that tan theta is going to be negative 6 over 6, so it's negative 45 degrees. In this example, I want to find the magnitude and direction of the vector given these components. We'll look at this one just symbolically rather than graphically, though graphically is often helpful to give you an idea of what's happening. Well, first writing it as components, it's negative 2, 5. If I want to find the magnitude, it's the Pythagorean sum of the components, so square root of negative 2 squared plus 5 squared, that's rad 29. To get the direction, I do the inverse tan of the y component of the x component. However, knowing it's negative 2 plus 5j, this would put me in the second quadrant. If I only do this calculation here, I'll be in the fourth quadrant. So to compensate for that, I've got to add 180 degrees. So whatever this comes out to be would be your direction. In this example, you are given a magnitude of 4 rad 3, a direction of 90 degrees. Finding the components, you just do 4 rad 3, cosine of 90, comma sine of 90. Cosine of 90 is 0, sine of 90 is 1. And it makes sense because if you're just going straight up, then the magnitude is all in the y component and not at all in the x component. And in this example, we want to find a vector of magnitude 8 in the same direction as the original. So here's the original 5, 6. I want to get one magnitude 8 in the same direction. So basically, I'm given the black vector. I want to get something like the blue vector. Well, what I do first is get the green vector. I get the unit vector. So to find the unit vector, I find the magnitude of this vector, which is square root of 5 squared plus 6 squared. So then therefore my unit vector in the same direction, I divide by rad 61. And now in order to get a magnitude of 8, I simply multiply that vector by 8. So I reduced it to a length of 1. Now I'll increase it to a length of 8. And here is my vector of magnitude 8 in the same direction as the original.